thank you very much for the invitation. And yeah, I'd like to tell you about some thermodynamic properties of quantum many-body systems after canonical quenches. And I'll be more precise what I actually mean by this later, but roughly speaking, you can imagine you have a system that is initially in equilibrium, and then we change some parameter so that the system is suddenly out of equilibrium, and observe how it evolves over time. And eventually, at least generically, we expect that it relaxes back to some new equilibrium state. And my goal is to characterize this state, so understand, for example, what its temperature is going to be, and under what conditions it's going to be a thermal state, and what role conserved quantities play in this process in particular. And at least looking at previous talks in this series, I realized I might be a bit of an outlier, because in particular, I don't do field theory. So all I'm going to tell you today is just non-relativistic quantum mechanics, textbook stuff, if you like. And so I thought it might be a good idea to give you a little bit of background information where these questions that I eventually want to address come from. And what concepts people have developed in this context to tackle this this puzzle of thermalization. What do I actually mean by this puzzle? So this is still very general, of course. We start from the phenomenological observation that macroscopic systems tend towards some sort of equilibrium state. So if you have something that has some macroscopic imbalances initially, and then you let the system evolve on its own, you leave it alone, eventually at late times, you're going to see that it's in some sort of stationary state, at least from a macroscopic perspective. So we usually don't perceive any macroscopic changes anymore. But we also know that the constituent atoms and molecules, or the particles that make up our system, are described by quantum mechanics. And on the energy timescales of our everyday life, it's non-relativistic quantum mechanics. And in quantum mechanics, the state will never really approach some fixed limit. It will never become stationary. And yeah, so the overarching research question is, how can we understand this emergence of macroscopic behavior from microscopic laws? And you might be thinking that, okay, non-relativistic quantum mechanics, amps and molecules, these are not really the most fundamental degrees of freedoms we could think of. So maybe you want to describe everything in terms of quarks and leptons and other particles, which would be very interesting to do, but it would also be more complicated, I presume. So maybe the idea here is that we acknowledge that the world is fundamentally quantum, but we are content with the length and time scales of our everyday experience. So we say, for us, we describe everything in terms of atoms and molecules, maybe. And then within this framework, people have developed a variety of ideas to understand how we can reconcile microscopic quantum mechanics with macroscopic statistical mechanics and thermodynamics. So some buzzwords are quantum chaos, ergodicity, the eigenstate thermalization hypothesis, and canonical and dynamical typicality. And I'll say a little bit about some of these things in the following. But what I also want to point out from the beginning is that there are still relatively few rigorous and general statements that you can apply to large numbers of systems or large classes of systems. So it's often postulates, conjectures that seem to work very well in practice, but we don't have any rigorous mathematical statements that connect, well, not many rigorous mathematical statements that connect quantum mechanics to statistical mechanics, let's say. So more precisely, the setups I want to discuss is that of an isolated quantum many-body system. So we have three main ingredients here: a Hamiltonian, H, that describes the degrees of freedom and their interactions. Then we have an observable A, which is the quantity we measure. And yeah, then the system is prepared in some initial state, rho of 0 here, which can be pure or mixed. And the nice thing about quantum mechanics is we can immediately write down, at least formally, what the state at any later time is going to be. So we can write rho of t is rho of 0 conjugated by e to the minus I ht. And then if we look at observable expectation values, so average measurement outcomes, those are given by the trace of rho of t times a. And I use this notation angular brackets subscript the state is my expectation value of the observable in that state. One particular important class of observable in the following will be conserved quantities. So an operator that commutes with our Hamiltonian is conserved. It doesn't change over time, or its expectation values and its measurement probabilities for outcomes don't change. And more generally, you can pick an eigenbasis of your Hamiltonian, which I denote by these ket n states, and then the corresponding eigenvalues are En, and then you can write down these expectation values in a basis, and you get these expressions down here. So we have, first of all, the energy difference in the exponential here, and then the matrix elements of your initial state and your observable in these eigenstates, and it's a double sum overall energy eigenstates. And then the first thing you can ask yourself is, what is this dynamics going to show in the long time limit? Because if it's going to settle to or if we want to show thermalization, it should better approach some sort of well-defined long time limit in some sense. But it's also quite obvious from this relation that this is not going to be some fixed state that we approach as t goes to infinity, because these phase factors in the exponential, they just keep evolving. So the best thing we can hope for is that we get something that looks stationary from a macroscopic perspective. So we could say that if we look at these expectation values here, they somehow appear to be stationary at very late times. So maybe they show fluctuations, but the fluctuations are very small, and they should decay as we make, or become smaller as we make the system larger and larger. And if this is the case, then the long time limit that the system is going to approach, or that these observable expectation values will approach, is the time average of this object. So let's have a look at this time average. And you see, if I time average here, the only thing that depends on time is this thing, and it pretty much acts like a Kronecker delta for these energies, En and Em. So what remains of this double sum is the following here. So I denote time averages by an overbar, and turns out that to get this long time average, we only have to sum over pairs of M and N where the energies are the same. So Em is equal to En. And an important special case is a system where we don't have degeneracies. Maybe this is again something you don't like in physics, or like from a mathematical perspective. We often like to work with highly idealized setups where you have exact symmetries and somehow often even very many degeneracies in your system. But this isn't really the generic setup, because in any real world experiment, you will have some sort of imperfections that break these symmetries. So it's not very unusual to have no degeneracies. And if you don't have degeneracies, then you can write everything in terms of such a diagonal ensemble. So there's only a single sum left, and we can define the state rho bar here from the occupations of our energy levels, rho and n. And then, a bar, the long time limit, is trace of this rho bar times a. And even if you have degeneracies, actually, you can still choose your energy eigenbasis such that the observable is diagonal in every energy eigenspace, so in every subspace that has a fixed energy. And in that case, you can also write everything in this form, although the diagonal ensemble will then become observable dependent. Right. So this will be the long time limit to confirm that this is actually, in some practically meaningful sense, a limit of the system. We should look at the fluctuations. So what is the deviation of one particular? I'll change the pen. What is the deviation of one particular realization from the average here? And then if we look at the variance of these, you can actually show on very general grounds that this is a small quantity, and a quantity that decreases with this effective dimension down here, which is defined here. So this quantifies how many energy levels, how many body energy levels your initial state occupies. And generically, you can expect this quantity to increase exponentially with the degrees of freedom of your system. So if you think of a truly macroscopic system with, say, 10 to the 20 degrees of freedom, this will be an effective will be a number on the order of 10 to the 10 to the 20th. So an extremely large number. And therefore, these fluctuations are typically very small. And the conditions that you need for this are very mild, although you don't know how long you'll have to wait for this to happen. So the statement doesn't make any assumption about how long it takes, but it assures you that eventually it will happen, although the time could be longer than the age of the universe, of course, in principle. So then the conclusion is that we can usually take it for granted that at sufficiently late times, expectation values will be very close to the time average for nearly all times. There will be revival events, but usually we say the system equilibrates, so it approaches some state that looks macroscopically stationary. But to characterize this state exactly is actually quite costly, because you would need to determine this diagonal ensemble here, which means you have to diagonalize your many-body Hamiltonian. But fortunately, we have other methods to determine long-term states from thermodynamics or statistical mechanics. So there are thermodynamic ensembles that we introduce, and that are, again, phenomenologically shown to characterize what large systems do at late times very well. So the conjecture from statistical mechanics, let's say, is that these long-term expectation values can be described in terms of expectation values of a thermodynamic ensemble. And for an isolated system, maybe you want to think of the microcanonical ensemble here. So you pick states from an energy window, or a window of states with energies around some macroscopic system energy, and you define a projection operator on these states, and then divide by the dimension, and this gives you your microcanonical ensemble. Alternatively, maybe you can use the canonical ensemble to describe this, which takes this form here. You have the partition function, and then e to the minus beta h. And I will not be very strict distinguishing between the two, building on results that again show under rather general conditions that these ensembles often give the same predictions about the behavior of the system. So if you choose the temperature in your canonical ensemble such that it reproduces the mean energy of the microcanonical ensemble, then typically this will also result in a very concentrated, narrow distribution in energy, and therefore the two averages typically agree. So, right, so a quick summary, let's say, of these two concepts. So by equilibration, I mean a system is initially, or can be initially, out of equilibrium, but then it will relax to some sort of stationary value or quasi-stationary value. And this stationary value can but need not coincide with the thermal prediction. By thermalization, I mean equilibration plus these two values agree. So the long time average equals the prediction from a thermodynamic ensemble. And yeah, so yeah. 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 Oh, if I have an example, so yeah, there are quite a few examples where you would say, so they are, then of interest as well. So integrable systems, for example, systems that have an extensive number of local conserved quantities. I'll say a little more about it in the following, but these are often, they go to some long time limit, but this long time limit is not described by the microcanonical or canonical ensemble, because you have to take into account these extra conservation laws. Yeah, often there are, I mean, often underlying symmetries are the reason for this. So then the symmetries would give rise to conserved quantities that are not typically taken into account in these thermal ensembles, and then you get the deviations. But there are other situations like these are called like quantum many-body scars or Hilbert space fragmentation, where there is no global symmetry, but still you have dynamically separate regimes in your Hilbert space, and these can also lead to violations of this thermalization principle. So the system will also, I mean, most systems that you can look at will eventually equilibrate, but again, the long-term state might not, or the predictions might not coincide with a thermal ensemble. That's the idea. Right. Yeah, so maybe to build a little more intuition or to maybe also get a feeling for how people used to approach this historically. So if you look at classical mechanics, the picture often used, I think, is that you have some chaotic system, many-body system, interacting many-body system will be chaotic in some sense, so maybe it exhibits sensitive dependence on initial conditions. And then we have this idea of ergodicity, that time averages equal phase space averages. So your system, the time the system spends in a certain region of phase space is proportional to the volume of that phase space region. And conserved quantities, conservation laws restrict somehow the accessible phase space. So in particular, you have an integrable system if the number of conserved quantities equals your degrees of freedom, because then you can reduce everything. You can go to these action angle coordinates and reduce everything to simple integrals, if you like. But the quantum mechanical picture is somewhat different, because first of all, time evolution in quantum mechanics is linear. So we don't have chaos in the classical sense. If you have two wave functions that are initially separated by some distance epsilon, the distance will still be epsilon, no matter how much longer you wait and let the system evolve. The time evolution is unitary. I said that multiple times already. So in particular, these occupations of energy levels are conserved as well, which means that in a strict sense, this diagonal ensemble will never be equal to a thermal ensemble unless you started from a thermal ensemble initially, because the thermal ensembles are defined by a specific choice of these occupations here. And if they don't agree, then the states cannot become exactly equal ever. Yeah, then we have the complication that in quantum mechanics, the Hilbert space grows exponentially with the degrees of freedom. So even if we have an extensive number of conserved quantities, like as many conserved quantities as there are degrees of freedom, we would still have lots of freedom in the Hilbert space to move around. And what is more, actually, in a Hilbert space or in a quantum system, we have as many conserved quantities as there are Hilbert space dimensions, because, for example, every projection operator onto an energy eigenstate is a conserved quantity. These are precisely the guys acting here, if you like. So just knowing all the conserved quantities, of course, this solves your system in some sense as well, but it also seems overly complicated and uses too much information to be useful in practice. So I cannot, and I don't need to, control every individual atom and molecule in my system. If I try to prepare a macroscopic system, I don't know, I try to heat water in my kettle, I don't need to set up every molecule in a precise microscopic state to do that. So yeah, but still building on such analogies, that there are a couple of concepts that people have developed. So one of them is this idea of quantum chaos, where you say that or people looked at systems that are classically integrable, and then you quantize them, and you observed, first of all, in this Berry-Tabor conjecture, was observed that if you start from an integrable system and you quantize it, then the energy levels follow a so-called Poisson distribution. So they're sketched down here, two examples. Whereas if you start from a system that is classically chaotic and you quantize it, then your energy levels follow a so-called Wigner-Dyson distribution. So that's the one on the right. And this is the BGS conjecture. And that the most notable difference is the behavior at zero. So these are your energy gaps, and then you see the frequencies of the energy gaps, basically. And you see that for the Poisson distribution, this goes to some finite value and actually to the maximum value as you make the gap smaller and smaller, whereas the Wigner-Dyson distribution implements this level repulsion mechanism. So as you let the gaps become smaller and smaller, the probability to observe such a gap goes to 0. And then people went ahead and also transferred this to many body systems that don't have a classical limit, and they observed the same phenomenon. So if you have a system that has Wigner-Dyson statistics, level statistics, then it typically thermalizes, whereas if you have a system that has Poisson statistics, then it typically does not thermalize. And so this is one indicator of chaos then, or was suggested as an indicator of quantum chaos. But yeah, what I should say is it's still important to resolve symmetry sectors in this picture. So if you have a system that has some other conserved quantity besides the Hamiltonian, you'll have to go to subsectors of your Hilbert space for these conserved quantities to actually evaluate the statistics, because otherwise you might get Poisson statistics or something that looks closer to Poisson statistics, even if your system is actually chaotic in that sense. So that's a nice analogy, but it doesn't really explain why or describe how this comes about that large systems thermalize. So the final concept I want to introduce here that has been developed then is the so-called eigenstate thermalization hypothesis, which aims to describe the actual mechanism that leads to thermalization in the long run. And the main idea is that if you look at physical observables, so something that we can measure experimentally, and you look at the expectation values of such physical observables in energy eigenstates of a physical Hamiltonian, so something that corresponds to, again, a system that we can implement, then the ideas or the conjecture is that these matrix elements will already be thermal expectation values. So this matrix element here on the left-hand side agrees with the prediction of a thermal ensemble, like the microcanonical ensemble here, at the energy selected by this level. So on the right-hand side, you have the microcanonical average over a window around energy En. So in some sense, the matrix elements are averaging themselves, if you like, in small windows around the energy of that level. And there are various different formulations of this idea. The one that I'm going to suggest you or I'm mentioning here is that you really want this to be true for every matrix element. So this is known as the strong ETH, which means that if you look at the maximum deviation for one particular matrix element from the thermal value, this maximal deviation should go to 0 as you make your system larger and larger. And if you have such a property and you know your system equilibrates, then you can actually conclude that it will thermalize, because remember, this is your time average, so your long time value. And if all these A and N are basically the same number ATH around the macroscopic energy of your system, then what you're left with is just a trace over your density operator. So the expectation values become the thermal expectation values. And this idea has then been verified numerically in a variety of cases. So you often see plots like this, where you're seeing the matrix elements, diagonal matrix elements on the y-axis here plotted against the energies. And then the different colors are different system sizes. The details don't really matter. It's some spin system observables in some spin system. And you see that as you make the system size larger, at least in the bulk of the spectrum, if you're not too close to the edges, you see that the observable expectation values start to concentrate in this region. So they become, the distribution becomes narrower as we make the system larger. And if you extrapolate to the thermodynamic limit, as it's done here, then you see it seems to go to 0 as you make the systems larger. But then again, there are exceptions to this principle, and often these are systems that then don't thermalize, but usually still equilibrate. So one possibility is that you have integrability, meaning an extensive number of conserved quantities. You can have many-body localization, so generalization of Anderson localization, quantum many-body scarce Hilbert space fragmentation, and so on. And again, you need to resolve symmetries, at least some of them. So here the common understanding is that you need to resolve local and continuous symmetries, or symmetries that correspond, so things that correspond to the particle number or the magnetization or the dipole moment of your system maybe, whereas you don't need to resolve non-local or discrete symmetries like momentum or parity or spin inversion. So this is in contrast to the level statistics indicator from the previous slide. There you typically need to resolve all of these. Here we only need local continuous symmetries. And so one of the goals of what I'm going to show you now, of the actual topic I want to speak about, is to understand the role of these conserved quantities better. Right. So this is my introductory part. I don't know, maybe I should pause for a second for questions, if there are any. Otherwise, I'll just carry on. So now the specific setup I want to look at is, the idea is that this is something you could actually, again, do in the lab. So you prepare a system in equilibrium first, in a canonical equilibrium state of this form. So your Hamiltonian initially is H tilde, and let's say we couple the system to a bath, which is at inverse temperature beta tilde. And then the idea is that at time equal to 0, we change some parameter here. So this is sketched by these arrows here. Maybe this is a magnetic field. I'm switching from one orientation to another one. And then I also remove the bath, and I just let the system evolve as an isolated system and see what happens in the long run. So the situation is described by a new Hamiltonian H here, which is H tilde plus GV, where G is the quench strength and V is the quench operator, so the difference, or the thing that changed when going from H tilde to H. And the convention will be that everything that carries a tilde is a pre-quench property or operator, and everything that has no tilde is a post-quench property or operator. So the system is, after this quench, is out of equilibrium and will evolve over time. And the key questions I want to address is what, first of all, if we assume it thermalizes, what is its temperature going to be? And can we say something about the equilibrium properties after the quench, knowing what the state initially was? And then I want to specifically look into the role of conserved quantities in this context. So let's have a look at the new equilibrium state first. So this is the post-quench Hamiltonian, and if we assume that the system thermalizes, we would expect that we can again describe it by some sort of canonical state, canonical density operator. I'm saying, I should say that. So at the moment, I'm not assuming anything about additional conserved quantities here. So maybe canonical ensemble isn't the best name, but for lack of a better name, I'm still calling it this way. I mean a density operator of this form, where the only requirement is that and this requirement fixes your temperature, is that the post-quench energy should be the same as the initial energy of the system, which in turn is the expectation value of your post-quench Hamiltonian in the pre-quench state, or in the initial state. Because we know energy is conserved in this setup, it's an isolated system. So this has to remain the same here. And this fixes the equilibrium state or the density operator then uniquely. But we don't know what this post-quench temperature actually is. So one goal is to determine what it will be. And the idea is that we can expand it in some perturbation series in the quench strength. So I'm making this ansatz here, if you like. And technically, the main step will then be to expand the pre-quench expectation values and the post-quench expectation values of first an arbitrary observable A here. And by choosing, for example, A equal to H, I can evaluate this relation here and then determine these temperature corrections here, order by order in G. But first what we need to do is we need to have a look at these two expectation values here. And I want to start with the the second one here, the post-quench thermal prediction. So the thing that we expect the system to evolve towards if it thermalizes. So what we do for this, so remember the operators of this form. And there are two parts. There's the partition function or inverse partition function and this exponential. I'm going to treat them separately first. So for the exponential, I subtract the beta zero coefficient, which, by the way, will turn out to be the pre-quench inverse temperature. Because you can imagine if this is the temperature that you observe if G is 0, so if there is no quench, so then of course the temperature doesn't change. So I'm subtracting this, and then I expand the exponential here as a power series and substitute my expression for the inverse temperatures, my perturbation series, which gives me overall a multinomial here that I have to expand and then work out what the various factors of the various powers of G are and what their coefficients are. And then I do something similar for the ratio of partition functions here. So this is the partition function at the pre-quench temperature and the partition function at the post-quench temperature. And their ratio can be written as a geometric series like this. So these Zn's here are some coefficients that follow from the expansion. I just didn't write them out because they're a bit lengthy. And then I can multiply these two terms together and sort by powers of G and eventually get something that looks like this. So these are now on the left-hand side, the post-quench thermal expectation values. And on the right-hand side, we see various averages involving just angular brackets. And this is a shorthand for this thing here. So this is also an expectation value of the post-quench ensemble, but now evaluated at the pre-quench temperature that we know. So whenever I don't specify the state in these angular brackets, then I refer to the post-quench ensemble at the pre-quench temperature. And based on this, I also define a covariance like this. And okay, you see, the first two orders here, or zeros, second and first, zeros first and second order. But in principle, I can give you a relation for arbitrary orders of this. And so what we've achieved now is that we have expressed these post-quench thermal expectation values at the post-quench temperature in terms of post-quench expectation values at the pre-quench temperature. So you can say that if you know the pre-quench temperature, which you might know from your experimental preparation procedure, you can measure what the outcomes will be at what the equilibrium values at the pre-quench temperature are, and then you can predict what they're going to be at the post-quench temperature. Right, so that's what I'm writing here. Once we know these temperature coefficients here, which we don't know yet, we could do this in principle to predict what's going to happen after the quench. Okay, so to get these corrections, we also need the other expectation value here, which is the initial expectation value of your observable. So the expectation value in the pre-quench ensemble at the pre-quench temperature. And in this case, again, I'm splitting it into the exponential operator part and the partition function part. And for the operator now, I look at this object here, phi of beta tilde, so phi of the pre-quench temperature, which is the product of the inverse exponential at the pre-quench temperature for the post-quench Hamiltonian and the exponential at the pre-quench temperature and the pre-quench Hamiltonian. And because the difference between these two Hamiltonians is our operator V here, or GV. I think there is a factor of G missing here. And since this V operator usually doesn't commute with H or H tilde, we have to write it as an imaginary time Dyson series. So you see phi occurs here itself again, and then we can solve this relation iteratively to get by every order in G, so that's why there should be a factor of G here. Get the terms for every order of G. And for the ratio of partition functions, I do again this geometric series expansion, where this now takes this form here, where these phi n's are sort of the nth order term of this phi beta function here. So it's a time-ordered product of these imaginary time-evolved quench operators. Yeah, and then you take the average. And then you can again multiply the two together, sort by powers of the quench strength, and obtain something that looks like this, where the upshot is that we have again expressed these now pre-quench expectation values at the pre-quench temperature in terms of post-quench expectation values at the pre-quench temperature, and some imaginary time correlation functions of them. Right. So now that we have these two expansions, we can actually use or come back to the plan that I suggested initially. So we substitute the Hamiltonian for the observable here, and then compare our post and pre-quench expectation values order by order in G. And what you find is this. So this is just a recap of what the perturbation series looked like. And then I told you this already. So at 0th order, no quench, we just find that the post-quench and the pre-quench temperature are the same. Then we get a first order correction here of this form, which was previously derived in this paper by Chiba and Shimizu using linear response theory. But then we can go to arbitrary higher orders in principle. So I'm written down the second order expression explicitly here as well, and can give you a general recurrence relation, how you can determine beta n from beta n minus 1 to beta 0 in principle. So that's the first goal accomplished. Now we know what the post-quench... yeah, so this was from the previous slide. So you look at this expression here. So it's some integral of this correlation function. I mean, because we average over it is the correlation function, and then yeah, second order integral here. Okay, so we have or we can predict, at least in principle, the post-quench temperature. Now we can try and test it. So the example system I want to look at is the transverse field easing model. So a 1D spin chain where we have these easing interaction terms and then a transverse magnetic field applied here. And I will fix H to be 1/2. And for the quench operator, in this example now, I also choose the magnetic field. So basically, I'm just changing the magnitude of H here by the quench, and I'm changing it. I'm adding 1/4, 1/2, or 1 to the initial, to the quench strength. And what I'm showing in the plot is the post-quench temperature as a function of the pre-quench temperature, where the solid lines are the numerically exact results. And then the various dashed lines are the various orders of the approximation. So at 0th order, you just get a straight line, beta equals beta tilde. And then first order is the orange dashed line here. And second order is the purple dot dashed lines. Yeah, and you see, first of all, that it seems to work better if you go to higher orders, which is reassuring. And it also reproduces... I mean, it reproduces it quantitatively. It also reproduces some qualitative features of the system or the post-quench temperature. For instance, the fact that the quench cools the system at high temperatures but heats it at low initial temperatures. So if you have high temperature means small beta tilde, and you see that then beta after the quench is larger than beta tilde. So the temperature has decreased. Whereas the other way around, if you go to later, go to larger beta tilde values, which means lower temperatures. Another example, different quench operator, is this here, where now I quench in the spin current. And this will be, I'm showing this basically because I want to use it later for the conserved quantities as well. So if I quench in the spin current, I also get that, it generally works better if you go to higher orders. The first order correction actually vanishes in this case, so that's why the gray and orange lines agree here. And in this setup, the quench always heats the system. So beta tilde is always larger than beta. Right. So this was temperature. And now the second question I want to address is the role of conserved quantities. And this is motivated by, first of all, the observation that conserved quantities are generally important in equilibrium statistical mechanics. I mean, we use them to define our microcanonical ensemble, for example. And they also seem to play an important role in these concepts of quantum chaos and ETH that I introduced in the beginning. But the subtlety is that quantum systems have an unimaginably large number of conserved quantities, for example, the projectors onto energy eigenspaces. So we have to find a criterion for which of these conserved quantities are actually physically relevant. Otherwise, the statement that we need to include conserved quantities is meaningless. And I'm going to adopt a very simple perspective here, which is basically, you can think of it like an operational definition. So I say if my conserved quantity Q is experimentally accessible, observable, and its initial expectation value or its pre-quench expectation value is different from the post-quench value, then it seems that the canonical density operator alone cannot properly predict this property of the system. So then Q must be a relevant quantity. Another way, because the conserved quantity, the expectation value isn't going to change, this thing here will always be a wrong prediction for this expectation value. And if we can measure it experimentally, then we can also observe that this system does not thermalize if it has this property. So the idea is now to test this condition here using our expansions for pre and post quench expectation values for the specific choice A equal to our conserved quantity. And by comparing this, so the full condition would be to compare it to all orders, but we can restrict to individual orders in G, and these are still necessary conditions for thermalization, because if it holds in general, it must, or if it is to hold in general, it must hold to all orders in the quench strength. The idea. So when we do this, the first order correction or the first order condition that we find is given by this expression here. So the covariance of the conserved quantity and the quench operator times the variance of the Hamiltonian has to equal the covariance of the Hamiltonian and the quench operator times the covariance of the Hamiltonian and the perturbation. What does it mean? Well, you can get a nicer geometric interpretation of this if you look at the covariance and interpret it as an inner product, because it has properties of an inner product. Namely, it's bilinear, so it's linear in both arguments, and it is also positive semi-definite, which means we can interpret it as like an inner product or a scalar product. And then this first order condition can be rewritten in this form here, which means we project both the conserved quantity and the quench operator onto the orthogonal complement of your Hamiltonian. So the space of all vectors that are orthogonal to the Hamiltonian. And the condition says that in this orthogonal complement, the conservation law and the quench operator have to be orthogonal to each other. So to illustrate it, think of this here being the Hamiltonian, this arrow, and then the orthogonal complement is the gray plane here, all vectors that are orthogonal to H. And then we can have, for example, a situation where V is the orange arrow here and Q is the blue arrow, and they are not orthogonal to each other. And if we project them onto the complement here, orthogonal complement, they're also not orthogonal to each other. So in this case, we'd say that the condition is violated. Whereas if we go here, then V and Q are actually orthogonal. You don't see it clearly, but this is designed in such a way that they are orthogonal to each other. But if we project onto the orthogonal complement of H, then they're no longer orthogonal, which means the condition is still violated. Whereas in this last scenario here, they may have some orientation that can be orthogonal or not. And if you project them, then they are orthogonal to each other, which means in this case, the condition would be satisfied. Okay, so how does this help answering the question of relevant or irrelevant conserved quantities? So if we now substitute specifically the case V equal to Q into the first order condition, so we quench in the conserved quantity itself, then what we observe is, or the condition takes this form then, so the variance of Q perp, the projection onto the orthogonal complement, must vanish, which means that Q and H have to be collinear. So we have to be able, we can write Q in this form here. And that violates the implicit assumption that Q should be an independent conserved quantity because we've basically just recovered the Hamiltonian. In other words, the condition cannot be satisfied in this case. So the conclusion is that any conserved quantity that we can, for which we have an experimentally accessible conjugate control parameter, will be relevant in an experiment where this parameter is quenched. So for example, if you have the magnetization and you can control the magnetic field, then if you perform a quench in the magnetic field, your post-quench equilibrium values will not coincide with the initial equilibrium, the initial pre-quench expectation values. And these conservation laws here, in principle, if they are experimentally accessible, they may still be non-local or discrete. For example, momentum could be something that you can change in the experiment, which is a non-local observable. On the other hand, they may still be irrelevant in setups where the quench operator is not equal to the conserved quantity itself. So in general, if there is some sort of overlap between the quench operator and the conserved quantity, it will become relevant. Otherwise, it may not be relevant, even though in principle it could be. That's the idea. Right. So then we can also go to higher orders. Maybe I can skip this. It's not. I mean, you get lengthier and lengthier expressions. In particular, for the second order, you now need a first order integral of one of these imaginary time correlation functions. But yeah, you can in principle again work out higher and higher order conditions for this. But typically, or at least in the examples I've looked at, the first two conditions would give you a very clear picture of whether the conserved quantity is relevant or not. So for example, coming back to this transverse field easing model, we have in this actually, so this is an integrable model, which means it has on the order L conserved quantities, and they come in two families. One of them are energy-like conserved quantities, so the Qn plus here. So Qn1, for example, is the Hamiltonian itself, whereas these Qn minus are current-like observables, so they describe transport properties of the system. And if you look at these, the conditions for these conserved quantities, you get the picture here. So first of all, this is the quench in the magnetization again, and I'm looking at Q2 plus and Q3 plus, so the energy-like conserved quantities, and they are, so the solid lines are again our initial and our thermal expectation values. So one is the pre-quench ensemble and one is the post-quench ensemble. For the condition to hold exactly, we would need the black and blue lines to coincide. And we see that this is not the case here, which means the condition is generally violated. And then the dashed lines and the dot dashed lines give you the corresponding first and second order corrections to these expectation values. So they test the first and second order conditions, if you like. If you look at the dashed lines only, the first order condition would be satisfied if they agree. If you look at the second order dot dashed lines, second order condition would be satisfied. And we see in this case, generically, these quantities don't satisfy, these conservation laws don't satisfy these thermalization conditions, so they are violated. Whereas if you were to look at the Qn minus, I'm not plotting them because you can actually show analytically that they satisfy some symmetry properties. So K here is complex conjugation in the product basis, which is basically time reversal symmetry. And you see that H is symmetric under the symmetry, but Qn minus, the Qn minus are all antisymmetric, and therefore you can immediately conclude that this trace here is always 0, which implies that these Qn minus don't change if you perform a quench in the magnetic field. But it changes if you perform the quench instead in this current operator. So now, because this current operator has overlap with the Q minus, conserved quantities, you see that here you now get a violation of these conditions as well for Q minus and for Q2 plus. We actually have that the first order conditions are now satisfied, but they're not satisfied at second order, and in particular, the exact conditions are also not satisfied as they should be. Okay. So then to wrap up, what I showed you is a recursive formula for the post-quench temperature, or how we can compute the post-quench temperature after canonical quenches in many-body quantum systems, and also more generally, once we have the temperatures, how we can use this to predict post-quench thermal observable expectation values from pre-quench or from thermal properties of the system at the pre-quench temperature. And I use this to derive necessary conditions for thermalization in the presence of conserved quantities, and these are recursively computable. And everything can be expressed in terms of equilibrium expectation values and imaginary time correlation functions at the pre-quench temperature. And maybe, the final point is that these constraints or the conditions are purely kinematic. So I don't need to know anything about the dynamics of the system. I'm not looking at time evolving properties, actually. And I don't need to make use of any of these concepts like quantum chaos or ergodicity or eigenstate thermalization, and so on. And that's it. So yeah, thank you very much. If you want to learn more about it, there is the reference to the paper. And of course, I'm happy to take questions.